Welcome to example 17. We have an example containing two capacitors. Capacitance 1, which is 6 microfarads, capacitance 2, which is 3 microfarads. And they're connected to a potential difference that's 18 volts. And we would like to find out what the equivalent capacitance, the charge, and potential difference across each of the individual two capacitors in a series and parallel connection. So we'll first start off by the series connection, and we need to draw a schematic diagram for that. So here I've drawn two capacitors that are in series, that's one after the other, between points A and B, which is a constant potential difference, VAB, which is going to be maintained. So the capacitors are both initially uncharged. So if you look at this from A, at point A, we're going to find that this capacitor, this top capacitor, and the top plate of that capacitor will acquire a positive charge Q on that plate. So this will become positively charged. And then that will, in turn, create an electric field that is going downward. So therefore, down here, there'll be an equal negative charge Q down on the lower plate. And remember, this is all neutral before. So if this is a negative Q, then down here on the lower end of this wire, right down to this now lower capacitor, but the top plate of that is going to induce a charge that is positive Q on this lower plate. And then therefore another electric field will be set up between this lower plate, and it will then induce a negative charge Q on the lower plate. And so as you can see, each of these plates will acquire the same charge Q. Charge is still being conserved, but each of these plates all have a net charge Q. What we will find different will be that the potential drop across the first capacitor and the potential drop over the second capacitor will be different because they have different capacitances. Okay, now we're ready to calculate the equivalent capacitance for the capacitors in series. And earlier in the notes, we derived the equivalent capacitance is equal to 1 over C1 plus 1 over C2. This is very similar to adding resistors in parallel, but we're actually adding two capacitors that are in series. So now we can substitute our capacitances. 1 over C1 is 6 microfarads, and we have C2 is 3 microfarads. And if we get a common denominator of 2, we will get 3 over 6 microfarads. And then we take the inverse of that, and we'll get 6 divided by 3, which is 2 microfarads. And you'll notice that this total capacitance of these two capacitors together, so if you were to replace these two individual capacitors with one capacitor, that capacitor would be less than any of these two capacitances. So now that you might recall because C equals epsilon naught A over D, and really what's happening is as you add more capacitors in series, the distance between the plates gets larger, and so therefore C gets smaller. So now moving on from here, since we know the total capacitance, we now can find the total charge in that one single capacitance. So what is Q of that capacitor? And you may recall that Q equals C times V. We had defined capacitance as charge divided by voltage. So we're going to use that equivalent capacitance, which we just determined, which is 2 microfarads, and multiply by the potential difference between A to B, which is 18 volts. That means the charge of that equivalent capacitance would be 36 microcoulombs. And since we just found the charge for the equivalent capacitance, we've also found the individual charges for both capacitance. So Q1 and Q2 is equal to that Q that we just determined, which is 36 microcoulombs. So each of these individual capacitors will have the same charge by conservation of charge. So now comes along, we have to find the voltage. We use the same formula, V equals Q divided by C. But if we're looking for voltage 1, then we're going to use C1. So divide 36 microcoulombs by capacitance 1, which is 6 microfarads. And we can do a similar thing for the second capacitor in series. That would be Q divided by C2. So 36 microcoulombs divided by 3 microfarads. And so that will give you, for the first one, 6 volts, and for the second one, 12 volts. And you'll notice that the capacitor that has the smaller capacitance will have the higher voltage. And that's because C equals Q over V, and as V gets smaller, C gets bigger. Or as V gets smaller, C gets bigger. And so these two voltages, if you notice V1 and V2, will add up to that total potential from A to B. So 6 volts plus 12 volts gives you 18 volts. And so now we're on to part B, where we would like to determine the equivalent capacitance and the charge and voltage across two capacitors that are in parallel. So let's go ahead and draw another schematic diagram for this configuration. So now we're looking at two capacitors that are connected in parallel. And in this scenario, the two capacitors will have the same potential differences, and the two charges will add up, Q1 and Q2. So these will have different charges if they're actually different capacitances. So why are the voltages the same for both capacitors and equal to the total voltage? If you look at this capacitors, the first capacitor and the second capacitor, their two upper plates are really all connected together and connected to point A. And so they're really just one equal potential surface. And if you look at the lower plates of these two capacitors, they're also all connected together and connected to point B. So B all the way to here and here all have the same potential. So really, each of these plates all have the same potential at the top and all at the bottom. So they will all have the same potential drop from the top plate down to the lower plate. So that means that you can automatically say the potential difference on the first capacitor and the potential difference of the second capacitor are equal to the total potential drop from A to B, which is 18 volts. However, what will be different for them will be the charges on the individual capacitors. Q1 can be determined by using C1 times V, and Q2 can be determined by using C2 times V. So if we substitute our capacitances in, that's 6 microfarads times 18 volts, and we have 3 microfarads times 18 volts, we could find out their individual charges. So for Q1 we'll have 108 microcoulombs, and for Q2 we'll have 54 microcoulombs. And you can see from here the capacitor that has the larger capacitance will collect a larger amount of charge. And you may recall this because C equals epsilon naught A over D. And so that as you increase the area, you'll increase the capacitance. And since C equals Q over V, as you increase the capacitance, you'll increase the amount of charge. So there's larger as you add more and more capacitors, and increase the cross-sectional area, you'll increase the charge. And also, you can find out the total charge by using Q equals Q1 plus Q2. So if we added 108 microcoulombs plus 54 microcoulombs, we will get a total charge of 162 microcoulombs. Let's go ahead and calculate that equivalent capacitance. The equivalent capacitance in series, or actually these are not in series, these are in parallel, is like adding resistors in series, but these are capacitors in parallel. So the equivalent capacitance is C1 plus C2. So if we add the two capacitances, we've had 6 microfarads plus 3 microfarads, and we have a capacitance of 9 microfarads. You'll notice that the equivalent capacitance in this scenario has increased compared to their individual capacitance, so the total capacitance gets bigger. And this goes back to this equation over here. As you add more and more capacitors in parallel, you'll find that the cross-sectional area will get larger, and therefore the capacitance of the total circuit will get bigger. And you could find Q now just simply by using Q equals that equivalent capacitance times the potential drop, which is 9 microfarads times 18 volts, which will give you 162 microcoulombs. So just to recap and reflect on what we've just done, for capacitors in series, in the first scenario, what we found was we got larger potential drops over the capacitor that was a smaller capacitance. So this had a smaller capacitance and yielded a larger potential drop. For capacitors in parallel, they all had the same potential drop. However, the capacitor with the larger capacitance ended up collecting the larger amount of charge. Now you don't really need to memorize these rules. I think you should just focus on understanding how capacitors work. Think of C equals epsilon naught A over D. that if you were to keep continuing adding capacitors in parallel, you'll have a larger cross-sectional area, and since then, therefore, the total capacitance increases. And as you increase the capacitance, you get more charge. Hence, charge is proportional to the cross-sectional area, which is proportional to the capacitance. If you look at capacitors in series, you could think of this in terms of the charges are all the same, right? But what we'll find is the capacitance gets smaller as you add more or more capacitors in series. And that goes back to this formula once again. As you add more capacitor in series, you could think the distance between the two plates is getting larger, and therefore the total capacitance gets smaller. But since C equals Q over V, we'll see the capacitance is inversely proportional to voltage. And so then as we decrease the capacitance, we increase the potential drop. So try to understand the formulas and understand how you can conceptualize these when you deal with capacitors in series and parallel. And that's it for this example.